All right. So welcome back again of today's class. Sorry about the hiccup. We were saying last week, that radiance is a function of multiple parameters. And these parameters are the wavelength in which the energy comes in, or the energy is being incident upon the surface of Earth and then being reflected and then being recorded at this sensor. The second one is the location, that is the location and the elevation of the Earth's surface, as well as the size of each pixels, that is the spatial resolution. Okay, so whenever we are talking about size of XY, we are talking about spatial resolution, and this spatial resolution is again connected to instantaneous field of view. If you can recall what is instantaneous field of view, it's just at a time through that angle that sensor can see or your eye can see. Okay, I can focus on an object. That's instantaneous field of view, or IFOV. And then radiance also depends on the temporal information. So temporal information has two aspects. The first aspect is how long the sensor is open, or for how long the sensor is recording the information. And another temporal information is how repeatedly the sensor can come back to the same position, the same location to record the information. For example, how frequently the sensor fly over Dhaka. Okay, if it's 16 days, the temporal resolution would be 16 days. Not the temporal information, but the temporal resolution would be the 16 days. And the angles. So angles are three aspects are involved in angles. So one is the terrain, another one is the relationship between or the angle between the terrain and the source, that is energy source, and another one is the angle between the terrain and the sensor. Okay, so multiple angles are also involved. And then if we talk about passive remote sensing, or if we talk about radar remote sensing, that is SAR, then we have to consider polarization as well, polarization of the back scattered energy. And then for all data, we have to consider radiometric resolution as well. So radiometric resolution depends on the bit. Okay, so it is calculated by the value of bits. So how many bits your sensors is. So your sensor could be built with 2-bit or 3-bit or 4-bit sensitivity. Okay, so what radiometric resolution does is it identifies how sensitive in how many scales your sensor can record information. It could be more than 1000 scale. That means it is sensitive to the 1000 scale. It could be in 255 scale, that is 256 scale, essentially. If we consider the 8-bit sensor, that means your sensor can sense in a scale of 0 to 255. Okay, so that is how radiance changes. The radiance that sensor sends, the value of radiance changes because of the changes of these parameters. So if one of these parameters starts changing, it's going to affect the amount of energy that is falling onto the sensor. So one excuse me, one common question or beginner's question that we have is the remote sensing, whether it's a science or art. Okay, in future as well, you will encounter this question wherever you go. If they are teaching you remote sensing, they will talk about this, whether remote sensing is science or art. So there is a video, but since this class is online, I'm not going to show you the video. I'm not going to play it here. Instead, I will send you the link of YouTube and watch it. by yourself. So I think that this video is from NASA, and in this video they talk about their project in Jupiter. So no human has been landed on Jupiter yet. I think no equipment has been landed there either. We are still flying on top of the atmosphere of Jupiter, and we're trying to sense it. So there was one project, and that intent project, JunoCam, captured multiple photos of Jupiter, and terabytes of information were coming in to the server of NASA. And at first they thought that, okay, so we will process all this information. This is science. This is classified. We'll process all this information and we will do all the works by ourselves. Later on, they realized that why there's so much information coming in. So we cannot process all this information. So why don't we make it public? And they did that. Okay, so they made all these remote sensing images public, and they utilized the citizen science techniques. So the citizens, the users, be that amateur user or a professional user, they started downloading these images. They started doing some scientific studies, as well as some of the artists. They started making stunning arts out of these photos. Very visual display. So yes, so from this example we can see that remote sensing is, you cannot put remote sensing in one single genre. You cannot say that remote sensing is just science, or you cannot say that remote sensing is art. You have to combine these two. Remote sensing is both. It's science as well as it's art. How? In science, you try to figure out the changes. You try to understand what's going on the surface, be it Jupiter or be it Mars or Moon. Okay. However, in the artistic perspective, what you do is there are multiple colors, there are multiple movements going on, there are multiple patterns being observed through remote sensing photos. So you try to manipulate these photos and you come up with different patterns. You come up with something very visually pleasing or intriguing. Okay, so these photos, they create some sort of sensation in your mind. So, and that's how they start becoming art. Science starts to transform into an art. So yeah, I will give you the link. See that video. It's very interesting. So the next topic that we're going to talk about is digital remote sensing. And from now on, whenever we will talk about, other than the history of remote sensing, we will be talking about digital remote sensing. And what is digital remote sensing? Digital remote sensing comes from how we capture the information digitally, or how we capture, whenever we capture any data or information digitally, we can, that means using the digital technology in remote sensing, we can say digital remote sensing. However, if you go back 100 years, 1920, at that time there were no sensor, there were no computer, no satellite. So at that time, all we had was analog remote sensing. There were film cameras, there were video cameras and photo cameras both. So you can go fly with an aeroplane and you can take a photo from up. That would be an analog photo. Then you can come to your dark room, develop the negative, and then print a photo from it. Okay, so that's pure analog. But now we have sensors, multiple types of sensors with different prices and capabilities. So now we talk about digital remote sensing. So this digital remote sensing, they can be both airborne or spaceborne. So what's airborne? Airborne is anything that is inside atmosphere. So if you fly a balloon, that's airborne. If you fly a drone, that's airborne because that's inside the atmosphere. If you go even higher than that, and if you are flying, let's say, with a plane, okay, so that's still airborne because you are still flying in the air. that is atmosphere. Okay, but if you go beyond this atmosphere, and if you fly a satellite or a shuttle, space shuttle, so at that time that would be spaceborne, because you went to space, and from space now you're observing what's going on the surface down below. However, the basic principles of these both, they are same. Okay, almost same. Why? Because if you go to space, there is no turbulence. So in space, everything is sort of smooth. Okay, there is no turbulence, nothing is shaking. However, if you're flying a drone, or even if you are flying with an aircraft, what could happen? You can fall into an air pocket, and then your airplane or the aircraft could drop few meters instantly. Okay, those who have flown, they might have had this experience that the plane went to an air pocket and then it dropped few meters. So if you are dropping few meters, that means if you can recall our last lecture's discussion about the instantaneous field of view and the size of the ground that we observe through instantaneous field of view. And if you can recall, with the distance between the surface and the distance between the sensor, if it's constant, then the size doesn't change. But if the distance changes, the size of the ground that is being covered by the instantaneous field of view, it changes. Okay, so space is very smooth. So the photos taken from a constant angle most of the time, and then it gives you with less amount of error, that is geometric error. Okay, what is geometric error? We will talk about it. However, if we use aircraft or airborne devices, at that time, because of the variability of the atmospheric pressure and all other things, all other parameters, the aircraft could have some turbulence, or the airborne device could have some turbulence. And because of this turbulence, it could make some changes. I mean, the photo or the data that we receive, we need to work on these more. They need more corrections. They need more processings. Okay. However, you do not have to be worried about this, because usually what we do is we deal with satellite data. Okay. However, in future, if you deal with airborne data, you have to keep that in mind, that aircraft cannot be constant, cannot keep constant angle, so it may change the angle, and also it cannot move into straight line, or it does not move into a straight line. So the satellites, they go straight round and round on the surface of Earth. But if you think of aircraft, it might go in a straight way, then have some turbulence up and down. Okay, and this is the surface of Earth. So it could happen like that. Also, if you are thinking of a path, then this is the path, and your satellite will go straight, okay, smoothly. But aircraft could go like this, even the drone. Okay, it could go like that. At the same time, when they are looking at some point, so this is the satellite, and then this is the ground, and you have fixed FOV, and this FOV is looking onto this area. Okay, and since the path of any satellite is straight, so it's going straight, the angle is constant. Okay, the angle is, let's say, 30 degrees, it's looking into 30 degrees, and the path of this angle is not changing. So you have a constant path. But if you are flying an aircraft, it might, at some point, due to the turbulence, it might look into this angle. Okay, and then it comes back to the original path, and then it looks now on the left. Okay, so you see, so because of the wobbling, do you know what is wobbling? Okay, wobbling এর বাংলা কি আমি জানি না। তুমি চেয়ারে যখন একটু পেছন দিকে একটু হেলান দাও, তুমি নাড়াচাড়া করছো, that is wobble. Okay, you are wobbling. তোমার ধরো চেয়ারের চার পায়া একটা চেয়ার, তো তুমি এরকম নাচাচ্ছ, so you are wobbling. So just like that, the airplane, if the aircraft is wobbling, that means it's also changing what it's looking into. Okay, so then you have some data. Let me erase all this. Now you have some data, and the data that you have got from the satellite is something like this, because it's went straight. But then the data that you have got from aircraft is something like this. Okay, why? Because your aircraft wobble at this position. So wobble means একটু বাম দিকে কাত হয়ে গিয়েছে এয়ারপ্লেন, সো কাত হয়ে যাওয়ার কারণে যেটা দেখছিল সেটা তখন এদিকে চলে আসছে। Okay, I think you have understood. So if you have any doubt or question, let me know. So how does this system work? How does remote sensing acquire images? Okay. So there are multiple things involved. So first off, the satellite is involved, then the source of energy is involved, and the Earth's surface is involved. So we find three stakeholders here. The first thing is the satellite, the energy source falling onto the ground, okay, and then this energy is being scattered or reflected or diffused at the surface of Earth. And this reflected energy or diffused energy is then falling onto the sensor and being recorded there. So what happens next is this satellite, it stores this information, and then it sends this information to a ground station. Okay, so ground stations are the stations with big dish antennas, and there are multiple ground stations all over the world, and they try to communicate with this satellite. And sometimes this satellite, they cannot communicate to the ground station directly. So what they do is they relay the information to a communication satellite, and then because the communication satellite is geostationary. What is geostationary? We will discuss it today. So just remember that communication satellites are geostationary. So that means that satellite, that communication satellite is in constant communication with the ground station. So the information being relayed from the satellite, remote sensing satellite, to the communication satellite, and then communication satellite further relay the information to the ground station. Okay, and then these ground stations are again connected to different controlling stations or control stations. Okay, so these ground stations, they again send this data, terabytes of information or gigabytes of information, to some control stations. Then these control stations, the servers, they store this data, they do some processing. Okay, so after the processing, they publish this information or the data, they release this data, and then we users, we download this information, or we collect this data, or we purchase this information, and then do the analysis, do the processing, do the analysis, and then finally we do the application. And based on the application, now we make changes in our policies. So that's how remote sensing works. So if I summarize this entire process, the sun is lit here, we have sun, the sunshine, all other energy source, they fall onto the ground. Okay, so the image that you see here is an ideal example of optical remote sensing. Just remember this is an example of optical remote sensing, okay, or passive remote sensing. Yes. Okay, so what happens is there is energy source. From the source, the energy falls onto the ground, get reflected, get recorded by the remote sensing satellite. Then the information become relayed to the communication satellite or directly sent to the ground station. Okay, ground station sends all this information to the control station, and the control station process this information, upload it to the servers for distribution. And then we users, we download that information, we process that information again. Okay, we do the pre-processing. That step is called pre-processing, and then we analyze this information and we publish the result. That is, we are applying. Okay, now we're in the application phase. We publish that information, and based on the result of that analysis or the publication of the result, now we make changes, the necessary changes. Okay, for example, there could be an study that Rohingya refugee camps are causing the deforestation in Cox's Bazar. So what you can do, you observe these changes using remote sensing, you publish the result, and government acts upon it. Government say that, okay, so we have to intervene and we have to make some controls to, stop this deforestation. Okay, so that's application. So, however, so there is also another important point in this picture, and what is that? This area, for example, is being recorded by this satellite. This information then sent to the ground transmission, okay, or ground station. Then that was being sent to the control point, uploaded to the server. We downloaded the image, and now what we have is, this is the image. Oops, sorry. So you see this image. This image is actually the image of this point. Okay, so this image represents the surface of this, the area of this, and these are divided. Since if you can recall, we were talking about raster data or the grid information. So all the satellite images, since they are photo, the digital photo, just like if I take a photo of you using my DSLR camera, so just like that, these are built on pixels. So if every individual pixels or cells, they are the representation of small area of these, the area that we are trying to study. Okay, so what are the information stored other than this representation? The coordinates. Okay, the pair of coordinates are being recorded. So every pixel, they know where their location is. Okay, what is their coordinates? They know that. Also, we also store the information of the shades or the color. Okay, or that means the gray shades or the color. These data are recorded in gray shades or the color. And how is that? Okay, how much gray or how much colorful the image should be? How do we understand that? We understand that information from the sensitivity. Okay, how much sensitive our data is. So this sensitivity comes from the radiometric resolution. Okay, so if you can recall my explanation from last week, if you have one, let's say one sensor which has sensitivity of 4 scale. Okay, so 4 scale is 2 to the power 4. That means 2-bit data. If the sensor is of 2-bit, sensor যদি 2-bit হয়, then you have 4 scale. That means you can have 4 shades of color or gray. Okay, one is the pure black, very black, just like that. Another one is a little gray, just like that. Okay, another one is a a lighter gray, which is like this one, okay? And then you have pure white, for example, okay? So based on the sensitivity, if you receive a lot of information, if your receiver gets saturated, then you have this pure white pixel. If you have a little less information than that, then you have this light gray pixel. And if you have even less and very little information, or very less than this much information, then you have this dark gray peak. And if you receive no information for some pixel or from some you know, some area, then your pixel will turn into a very black one, okay? Because black means there is absence of information. So one more other thing that I would like to draw your attention to is the ground resolution cell, or the resolution cell, okay? Excuse me. So this one makes the resolutions, this small area, okay? These are being represented by this every single pixels, okay? That is one aspect. Another aspect is that, for example, just for the sake of argument, we are saying that this is the instantaneous field of view. So the instantaneous field of view is covering, one instantaneous field of view is covering this area, okay? That means, and this one is being represented by a by individual pixel in our image, okay? At the same time, the area in reality which is being recorded by instantaneous field of view, we call it ground resolution cell. So the same, if it's angle at the satellite, we call it instantaneous field of view. The instantaneous field of view, the area or the information of the area that it collects is called ground resolution cell. And then when we transform it into a photo or a scene, satellite image scene, and then if that area is being represented by in that photo by a pixel, we call it pixel. Okay, so their same element is having three different names based on the perspective. If you are talking about from data perspective, if it's in your data, you call it pixel. If you talk from the sensor or the satellite perspective, if it's in the satellite, you call it instantaneous field of view. If it's in reality, okay, this pixel is covering this region, for example, okay. If it's in reality, this is the reality, so you call it ground resolution cell. Three different definitions. We'll come back to this. So yeah, so this is, I have already discussed this part. You have sensor, then what you do is you send it to the ground, and once the information is sent to the ground, and then you download the information, and then this is user part, okay? This is user part. So this part, this one we already discussed. We have already discussed this in previous slide. So now you are user, you have downloaded this information already, and then now you are processing this information. And what are you doing while you are processing this information? At first, what we do is we pre-process our information. That means we try to do some corrections. There are some errors still. We try to fix these errors. How do we do that? We do radiometric and geometric calibration and correction. And what are these? We'll discuss that. In fact, at the end of this course, you will be doing radiometric and geometric correction using satellite images. And then what you do is we observe, we make some visual observations as well as analysis. From this visual observation, we try to understand the scene that we have. And in the analysis part, we try to do some analysis. We try to find out inside information, okay? Inside information of the scene that we have. That is what's going on there, how much land cover has changed, how much urban area has transformed, into something else, or how much water bodies or vegetation has transformed into urban area. This form of this sort of analysis we perform. And then finally, once we have find out some information, for example, most of the vegetation in Dhaka area has transformed into urban area, examples like that, then what we do is we distribute the information. Okay, and how do we do that? We can upload our result or upload our byproduct of the satellite image into multiple servers, for example, Geodash, okay, or something else, or Diva GIS. In these platforms, we can upload that. We can publish our information into multiple journals, okay, as an article. We can write books. We can develop reports, and the governments and relevant stakeholders, they can act based on these reports or scientific publications, okay. And other users, they can always access the information that you have uploaded to another distribution server, okay, or distribution center, for example, Geodash. Other users, they can access this information and they can do further analysis. So in digital remote sensing, what we will talk about, or what do we talk about, is we talk about the instruments that are being mounted on the satellites to detect the reflected radiation. We also talk about different wavelengths. In fact, I will ask you to memorize the wavelengths, okay? Different wavelengths, not to worry, they are just few ranges. And then in what it does is this remote sensing then transmits back to Earth. We already have talked about this, okay? And then two types of information, two types of processing is required or being used to make them usable. One is signal processing and image processing. So from these, we will talk about image processing. So first off, let's talk about the sensor. So there are multiple types of sensors, okay? So, and the types of sensor depends on where they are or depends on their altitude. So the first one we talk about is ground observations. For example, you can go with your GPS, or your phone might have GPS enabled. You can go anywhere and you can take photos. So once you come back, now if you would like to upload them into OpenStreetMap, all you have to do is you have to access the GPS information, and you can upload to some platform which is a sister platform of OSM, and it can give you a very similar view of Google Street View, okay, based on the pictures that you have taken at multiple locations. So in this example as well, what you are doing is you are doing remote sensing, but instead of going up, instead of looking down from up, what you are doing is you are looking at the horizon. You are taking photos of the horizon, okay. You are taking photos of your surroundings. So that is called ground-based. So this ground-based, in this ground-based observation or ground-based remote sensing, you are very close to the ground. But this is a very easy way, a typical way of taking photos. So in remote sensing, we hardly talk about ground-based remote sensing, okay? Instead, we focus on the other two types of remote sensing. And these two are airborne and the spaceborne. In the airborne part, there are two types of platforms. One is the low altitude data. One platform collects low altitude data, for example, drone. Another one collects high altitude data, for example, aircrafts. Okay, and then we move on to the spaceborne, and this is the one that that has created the buzz. Okay, and also this is the one which is highly talked about. The most of the data were collected using these spaceborne remote sensings. And these spaceborne remote sensings as well, they were again divided into multiple types based on their height and based on how they move around or how they function. Okay, so there are polar orbiting data, or there are low Earth orbiting satellites. So low Earth orbiting satellites, they are very low to the, they have very limited, very low distance between Earth and them. So they are above, for example, 400 kilometers from the surface of Earth. Okay, so their orbit is they are at the lower orbit of Earth. They are in the space, but they are very close to the Earth's atmosphere. Okay, then we have middle Earth orbiting satellites, or MEO. Okay, so this one is a little bit farther away from Earth's surface. Then we have GEO, which is geostationary Earth orbiting satellites, or we call them simply geostationary satellites. They are GEO. Okay, so these GEO are more than 35,000 kilometers away from the surface of Earth. So yes, however, basic types, there are three basic types: ground-based, airborne, spaceborne. Yeah, so I have already discussed this, I think. So ground-based, we can go up to 50 meters. Airborne platforms, they can go up to 50 kilometers. There are multiple devices: airplanes, helicopters, high-altitude aircrafts, balloons, etc. Okay, so you see ground. Also, when I'm saying this, you have to look into this word, okay, ground truth. So this word is very important. This data, this ground truth data, is collected by using ground observation or ground remote sensing. Okay, so we will come back to that, how ground truthing is important, how it is vital in remote sensing and GIS. We will talk about that later. So airborne platforms, they can go up to 50 kilometers. Okay, and then we have spaceborne. Spaceborne are shuttles, rockets, satellites, etc. Okay, they starts from 100 kilometers to 36,000 kilometers. So the shuttles, they can reach up to 300 kilometers. So you can put 300 there. Space stations, for example, JEDI. JEDI is on International Space Station, okay, ISS. So they stays from 300 to 400 kilometer above the ground. And then we have low-level satellites. For example, Landsat is low-level satellites. So Landsat, Spot, MOSS, all these things are ranging from 700 to 1500 kilometers. Then high-level satellites, for example, Bangabandhu satellite, it is located very close to 36,000 kilometers, okay, from the surface. So another example, if we can now compare it with our atmosphere. So you see that we have troposphere here. The planes are flying, the balloons, they are reaching up to this point, troposphere, a little bit up. Then in the troposphere, then we have this tropopause. Okay, I think this is the temperature line. Yes, so temperature is decreasing and then it's again increasing. Okay, so these supersonic planes, they are flying very close to 50 kilometers up from the ground. Then then if we go to the 100 kilometers, then we are talking about now the space shuttles. Okay, and then from the 400 kilometers to 1500 kilometers, or even 35,000 kilometers, we are dealing with the satellites. Okay, our satellites are there, and the meteors, they come into the atmosphere, so they happen to be in the very top of the atmospheric level. So that's 100 kilometers. Okay, we have these polar lights. The polar lights, I think that's aurora if you go to northern hemisphere. And then we have clouds in this region. Okay, and we have Mount Everest here. So now you can have some idea how the remote sensing types are distributed all over the space and the atmosphere. So for the ground truthing, or for the ground remote sensing, these are the ways that we collect our data. Okay, so the ground truthing data, among the data of ground remote sensing, one important aspect or one important category is ground truth or ground truthing information. Okay, and these data are collected within 0 to 20 meters of the surface of Earth, not the mean sea level, but the surface of Earth. So these are the devices that can take this data. One of them could be the spectrometer. So this one is called spectrometer. Okay, so what a spectrometer does is, just like satellite images, it can take it can take the spectral signature of the objects. For example, you have one spectrometer and then you hold it on a leaf. Okay, একটা গাছের পাতার উপরে তুমি ধরলা. If you hold it and if you start taking that signal, then it will give you some spectral signature like this. And what is spectral signature? We will discuss them as well. We have to be just patient for now. Okay, and then you take one Landsat image and you see one pixel which contains vegetation, and then if you find out the spectral signature of that Landsat image, it will also look like something like this. Okay, however, why this is important? Because spectrometer can find out the spectral resolution of every single object. That means if you have leaf from a mango tree, you can record the exact spectral signature of that mango leaf. If you have a pine leaf, you can record, or a pine needle, you can record the exact reflectance, that is the spectral signature of that pine needle. Okay, if you have some mineral, you can find out the exact spectral signature of that specific or respective mineral. In that way, you can actually have a database of everything that you have got. Okay, excuse me. You could have a database of every possible spectral signatures. That means spectral signature of, let's say, water of a pond, spectral signature of water of spring, spectral signature of water of river with low sediment, high sediment, medium sediment. Okay, the water or the spectral signature of river water with turbulence or without turbulence, a calm river, something like that. Okay, if you are talking about leaves, then you can have a spectral signature of mango leaves, jackfruit leaves, pine leaves, teak leaves, and so on. Okay, all the trees that you could have in your locality. And then when you download your satellite data, what you can do is, based on these spectral signatures, you can automatically map the surface of the ground. Okay, so the software will automatically try to match of the spectral signature that you have in your satellite and the spectral signatures that you have on your database. So you see, I say the spectral signature singular form that you have in your satellite. That means that every pixel has individual separate spectral signature. So if one pixel has specific spectral feature, for example, like this one, okay, on left, and then it will be matched with the spectral signatures that you have in your database. Okay, and then it will find the closest one, and the closest one that it finds is on the right side, which is the spectral signature of vegetation, let's say from a mango leaf. So that means the software will identify this specific pixel as it's a mango tree. Okay, so all the pixels matches this spectral signature of mango tree from your database will be classified as mango tree. So that's automation. Okay, that's the automatic process. For that, of course, you have to collect a lot of data. And in USA and Europe, they have already collected all their information. So especially in USA, if you go to USA you will have multiple inventories of spectral signatures. So they have spectral signatures of all possible entity from the reality. They have already collected those. They stored these into their database, and then they are still continuing to collect even more and more information. Okay, so this is also spectrometer, another form of spectrometer. Then we have, of course, GPS devices. Why GPS devices? This is one sophisticated GPS device or triangulation machine. They cost around 35,000 US dollar per device. So why this one is so expensive? Why do we need such expensive device? Okay, why? Because this one gives you more accurate and precise information. That is the more accurate and precise latitude and longitude information, locational information. All right. And why is that necessary? Because in your satellite data, for example, the left spectral signature, this spectral signature in the satellite data, it was recorded at some specific location. If you can recall this slide, that this one collects pixel coordinates. So every pixel has their own specific unique pair of coordinates, okay, which is related to the actual coordinates, or which falls onto the actual coordinates to match, just like Lego, to match each other. Okay, they always fall onto each other. So that's why when we go and we try to collect some data, of course, we need the information of this location. Okay, if we want to say that, okay, so this is our satellite image, for example, this is our satellite image, and now we want to verify whether these images were classified correctly or not. So at that time, we have to have some data from real world, the actual data from real world. So what we do in that case, that we go to our study area, and then we go with spectrometer, or we just go with our GPS devices. We sit on it or stand on it, and we say, okay, so this one is vegetation, this is forest. And then in our pixel, in our image, we try to identify the same pixel, and we try to find out whether this pixel is classified in forest or not. If it's not classified in forest category, then we say, okay, our classification is wrong. We have done some mistakes. Okay, or the classification algorithm that we have used have done some error. So this should be fixed. So we go back, we do the entire thing again. We try to improve our result, and then we come back and we find out that, okay, so in this location for some X and Y coordinate, this is X and Y coordinate. So in this X and Y coordinate, we found forest. Now we have done the classification again. So this pixel is of X and Y coordinate. Then we check again. Now we find that, okay, so this is classified into forest. Okay, so based on such technique, we can say that the satellite image that we have processed or we have classified, that one is giving you the accurate information. Okay, because we have tested it against our ground truth data. So this is called ground truth data. You are checking whether the information, I mean, it's a true information collected at the ground. So another way of memorizing or remembering or recalling its definition could be such. It's a true information collected from the ground. So ground truth information. Okay. So in the ground, we can also, so in the airborne, we can collect the data in multiple ways. If they are in low-level data, we can fly with balloon. We can fly ourselves in balloon, or we can send some sorts like weather balloon, and then we can send them up in the sky, and then we can collect remote sensing data, or we can send some drone as well. Then we can also fly with aircraft, collect high altitude data. After that, we can use our space shuttles to go beyond our atmosphere, Okay, and finally, we can use satellites to collect even more information from even further distances. Okay, so Earth orbiting satellites, they have multiple ranges. If we talk about low Earth orbiting satellites, they actually remain from 200 kilometers or 400 kilometers to 2000 kilometers. Okay, so they revolve around the Earth. And the geostationary satellites, they are located at the farthest point. Should I say farthest? Farthest, maybe, F-A-R-E-S-T. Okay, so they are the most distant satellites that we have in the orbit of Earth. Okay, so they usually remain at 35,786 kilometers, but just to round this value, you can say that they are orbiting by staying 36,000 kilometers away from Earth. So now we have, in this example, we have types of satellites or types of remote sensing from two different aspects. The first one is optical data. So I will draw a line. So this is the optical data. This part on the left side of this red line contains the optical data, and on the right side it contains the radar satellite. Okay, so in the optical data, most of the remote sensing data, most of the historic remote sensing data were collected in optical form. So what's optical form? Optical form is just like you take a photo using your DSLR or phone camera. So that one is optical data. Okay, sun is lit, or there is another energy source. That energy source is falling onto you, and then I am the photographer is taking a photo of you. How? Just like our eye works. Okay, how do we see? We do not see in the dark. Why? Because there is no energy. Okay, there is no energy bumping onto each other, different objects, and that energy is not falling onto our eye. Okay, so we cannot see. But in daylight, we can see. Why? Because the sun is up, it's radiating energy. That energy is falling onto different surfaces, and then they are falling, these reflected energy from different surfaces, they are coming to our eyes. Okay, they are falling onto our eyes, and that's how we see. And the optical, because you see the eye is called optics, right? There are some optical nerves and some sort. So similarly, these satellites, these sensors, they are also called optical sensors, and the data that they collect are called optical data. Okay. Now, so passive and active, I will discuss in the next slides. So in this optical data, you can see we have aerial photos. Okay. However, in these aerial photos, this is the third category of remote sensing. Okay. So we have aerial photos, then we have high resolution optical satellites, which are actually low orbiting satellites, low or medium orbiting satellites. Okay. And then we have low and medium resolution. Someone is talking, let me mute everyone. Yep, I think he or she has muted him or herself. So in this medium, so we have high resolution optical satellites orbiting in the low orbits or medium orbits. Then we have low to medium resolution satellites, which can collect data, regional data nationwide. For example, it can capture entire Bangladesh. Okay, they are located in the medium orbits or geostationary orbits. Okay, then now these low orbit, medium orbit, then geostationary, then airborne, ground-based. These are based on the altitudes of the satellites. Okay, these types of satellites are based on the altitudes of the satellites. Now, what is the energy source? Based on the energy source, the remote sensing satellite could be two types, sorry. One is active remote sensing and passive remote sensing. I think next one is that, yes, active remote sensing and passive remote sensing. But before we talk about this, we have to also think about what sorts of information that it collects, okay, or at which wavelength the data are being collected. If the wavelengths are very short, okay, very short, then these are optical data. Okay, so based on the size of the wavelengths, we can categorize the remote sensing into three groups. One is optical, then it's laser, so laser, and then there is radar. So radar collects, it uses radio signals, okay, so even longer wavelengths. And in optical, it uses the wavelength that is visible to our eyes, okay. So, and our eye can sense from 400 to 700 nanometer, okay. So 400 to 700 nanometer. So these optical sensors, they sense this amount of energy. They sense the energy which are from, let's say, 400 nanometer till 1000 nanometer, something like that, which are very close to the close to our optical range. Okay, the spectrum that we can sense through our eye. And the laser, it uses different technology. It uses laser to identify the objects. So based on the wavelength, we can categorize the entire remote sensing into three groups. Based on the altitude of the sensor, we can divide our remote sensing into three groups. Okay. Based on the source of energy, we can divide our remote sensing into two groups. So you see, I have already discussed or mentioned three ways to divide the remote sensing, or three ways to find the types of remote sensing. Don't forget that. Okay, it could be in your final exam. So based on the energy source, we have passive and active remote sensing. And just the way they are named, passive and active. So passive means it's indirect, it's not direct. That means I do not have any energy source. The satellite which is collecting, or the sensor which is collecting the data, it does not have any energy source. Instead, what it does, it relies on a different energy source. Okay. And then what is these different energy sources? They could be sun. Okay. Most of the time it's sun. Okay. So that's why we put it just sun here. And the active remote sensing is, and then there could be some other passive remote sensing, okay, which is when the energy source is not really sun. Can anyone give me any example of such? The passive remote sensing data when the sun is not the energy source. The next slide would be our last slide for today. কেউ কি আমাকে বলতে পারবে যে এমন একটা প্যাসিভ রিমোট সেন্সিং এর ডেটার উদাহরণ যেটার এনার্জি সোর্স হচ্ছে সূর্য নয়?
So can you use lunar energy for remote sensing?
Sorry, what sort of energy?
So lunar energy, sir, mooner light take use kore passive remote sensing.
Okay, very close. Lunar energy, very close, but lunar energy is quite weak. So our eye have difficulties to, unless it's full moon, our eye has difficulties to observe using the lunar energy source, right? And the satellite, they are far away. So there could be lots of interference between the Earth and the sun, sorry, the sensor, the satellite sensor. So one quick example would be the night light images. How many of you have seen night light images? So sometimes you will encounter on internet that there are some map of nightlife. So in this map, all the cities are well lit, they are bright, and the other regions where there is no city, they are dark. Have you seen these sorts of maps?
Yes, sir.
Yes,
This is
right?
basically
So
when you're flying from plane during the night, you can see this kind
you
of.
can also see that. Okay, so just like that, there are some night light satellite data. So one of the satellite is DMSP. Okay, so this nightlight satellite data, they do not use, they are still optical remote sensing, they are still passive remote sensing, but they do not use sun's information to collect their energy. They rather, instead, they use the energy being radiated from the surface of Earth. That is, the energy being radiated from different light source. And this is very important. Why? Because there are lots of economic studies. Economic studies means studies that have been done in economics. Okay, these studies, they found a very good correlation between the night light and the poverty. So if there are night lights, okay, if the range of night lights is very high, that means that city or that region is less in poverty than the other region. Okay, so if you look into this, and you will find all the rich cities, all the economically well-off cities or nations, they have very good, uh, night light satellite images. That means satellite images, these are full with night lights to support this idea. Okay, and this study was actually done in and it's a very good study. So to identify poverty, you do not have to go around, you do not have to go from door to door, and you do not have to really study GDP, because GDP is very much biased. You can easily access this nightlight data and study poverty, how much poor our people are, or how much poor the African nations are, or how much rich the European or Western nations are, something like that. Okay. Uh, Even using this data from city to city, you can understand the distribution of wealth. So how the wealth is distributed. Okay, you can identify this information within a region or within a country or within a district. And the active remote sensing, what it is. So in this example, the energy is being radiated from the sensor, or the sensor has some parts of in the instrument from the sensor. It radiates, it releases the energy, and that energy falls onto the ground and comes back to the sensor. So the example of these is radar and LiDAR. So this is active radar satellite, laser satellite active, optical passive. Okay, now you can connect between the wavelength and the source of energy. These two types of remote sensing, you can connect them. If the wavelengths are very small, these are optical remote sensing that we are talking about. Okay, and if wavelengths are longer, these are radar satellite or laser satellite that we are talking about. So this is the example of passive and active remote sensing. So in the passive remote sensing, the energy falls from the sun and then they get reflected. In the active remote sensing, the sensor releases the energy and then this energy gets reflected and recorded by the sensor. All right, so that is all for today. Anyone have any question?
Assalamualaikum, sir. Hello.
Yes, Arif.
Sir, হ্যাঁ গ্রাউন্ড ট্রুথের ক্ষেত্রে স্যার আমরা দেখছি স্যার যে একটা এলাকার স্যার মানে একটা এলাকা যদি আমাদের স্যাটেলাইট থেকে স্যার ইমেজ নেয় তাহলে স্যার গ্রাউন্ড ট্রুথের ক্ষেত্রে স্যার প্রতিটা পয়েন্টে কি আমাদের মানে লঙ্গিটিউড এন্ড ল্যাটিটিউড নিতে হবে নাকি কয়েকটা পয়েন্ট নিলেই হবে?
নো, নিতে হবে না, কয়েকটা পয়েন্ট থেকে নিলেই হবে।
আচ্ছা স্যার।
Okay, any other question? Okay, যদি কারো কোনো প্রশ্ন না থাকে, I'm going to stop sharing and then stop recording, and that's the end of today's class. Thank you.